Okay. So now with the rules that we know, right? Stress A, right? Stress at point A, right? So we're going to find stress at point A, point B is equal to Vy over Izz multiplied by Qz for point A divided by T for point A, right? So this is the formula. And then the other formula is the shear stress at point B is equal to Vy over Izz Qz for point B, and then thickness for point B. And the last equation is tau max is equal to Vy over Izz Q Z max divided by T. Okay. So what I'm trying to highlight is you immediately, if you see this problem, you're okay. Let's go. Okay, we're gonna find second moment of area. You boom boom boom. You just keep on. No, you don't do that first. Okay, you look at the distribution and like what is stated in rule number 1, right? Rule number 1, constant, 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 right? So the first thing we have to find is we have to find the ratio, right? You have to find the ratio, or not the first thing, we have to find the ratio of Vy over Iyy. Okay, you have to find. So if you have this value, sorry, Izz, if you have this value, you don't need to know what is Vy, you don't need to know what is Izz. And that is possible because we know that tau max now is 10 times 10 to the power 3, right? The only thing we have to identify are your Qz max. What is our Qz max? Okay, what is our Qzb? And what is our Qza? Thickness is easy. Okay, thickness is it. So as you can see, the first moment of area are the one that's very sometimes can be confusing to find. Okay, so these rules, these 4 rules, right, they are set. This one belongs to first moment of area. This one belongs to first moment of area. This one belongs to first moment of area. Okay, so the first moment of area controls everything. Now, then what makes this problem more confusing is this now. So I'm going to copy. Let's look at this structure. Right? Can anyone tell me? So I'm going to draw our centroid. Okay. So we're going to draw centroid. The centroid is exactly going to be here. Right? So this is our centroid. Can anyone tell me, is this a box beam or wide flange? Anyone? Or is a combination of both?
Combination.
Yeah, absolutely right. It's a combination of both. And why do you say that?
Well, it's the top half is clearly a box, but the bottom half has 2 flanges. So
Right? So you're right. So you are analyzing based on the centroid, which is the what? The centroid is also known as the datum. Yes or no? Absolutely right. Okay. Right? And the rule state what? The analysis start from the datum, and the first moment of area cannot cross the what? The datum. You're absolutely right down there. So if I were to cover, so I'm going to draw something. Okay, hold on, people. I'm going to I need to get a hold on. Where is it? I need to get a cover. A rectangular box will do for me. Okay. Let me elaborate. If I were to cover the bottom, right? So we know that at the top, by looking at the top now, right, it's equivalent to a what? Box beam, right? So when we deal with box beam, the next thing is we have to design the shear flow. Okay, so we will have a common start over here. Bad color. We have a common start over here, right? And then one Q go over here and one Q go over there, right? And then it comes here. So that is my point B, right? So now if we were to look at our bottom, so we know at point B we share a common what? We share a common start point over here, right? One arrow goes to the left and the other one goes to the right. Now if we look at the bottom, if I can, how come I cannot copy now, you cheeky sod? Microsoft. So now if we look at the bottom now, so again I'm going to draw my centroid. Okay, so this is about my centroid, right? Now for point A, I'm going to cover the top now, right? Now the bottom has a configuration of what? White flange. And for this case, what you will see, right? What you will see is the Q goes to here, right? So this is your Q, this is your Q, and then they finish at two different. So this is endpoint number 1, and this is endpoint number what? Number 2, right? So 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 the top is a box beam, the bottom is the what? White flange. Okay, so it's 2. So how does this work out? Okay, how so you guys will be asking, yeah, okay, so what? Okay, so now let's look at the top first. Okay, so I'm going to copy this whole thing. Any questions so far before I go on? Anyone? Are we okay? Okay, so I'm going to do the top first. Let's find the shear stress point A. Okay, so sorry, point B. So let's find the shear stress at point B. Okay, let's find the shear stress at point B. So because at point B, right, the start is from the center, you have 2Q, splitting up, you have to consider this entire area. Okay, so you have to consider this entire area now. Okay, you all can see, right? You have to consider the entire area. So when that's the case, to find the Q, okay, we are going to find the Q for point B. So this is equal to width multiplied by depth multiplied by y bar. So the width over here, if I were to remove some of, so it's 2 minus 0.3 minus 0.3. The depth is 0.2. The y bar is 3 because the entire thing is 3. So 3 divided by 2 minus by 0.2 divided by 2. So the y bar over here, so is 2 minus 0.3 minus 0.3 times by 0.2 times by 1.5 minus 0.1 close bracket is equal to 0.392 inches to power 3. Okay, and then the thickness at point B, so this is our thickness, right, is equal to 0.2. So next we find the shear at point B, right? So before we find the shear at point B, I want you to have the habit to do this, okay? So this is a box beam. Okay, so this is a box beam analysis. So you write down that this is a box beam analysis. And I want you to have the habit to say that this is equal to what? 2Q. Because 1Q go to the left, the other Q goes to the what? To the right. So when you write the shear at point B, you have Vy over Izz. Then you multiply by your QB, 0.392. Is this point B? Yeah, 0.392. The thickness is 0.2. And then you multiply 2 down here. The 2 down here because of what? You have what? 2Q for what? Box beam analysis. Okay. So from here, this will be equal to Vy over Izz 0.392 divided by 0.2 divided by 2 is equal to 0.98. So it's equal to 0.98. Okay, 0.98 Vy over Izz. Are we clear? Okay. Oi, something bad happened. Maybe it does not like the copy. Okay, so it's 0.98 Vy over Izz. Okay, so this is for the shear stress at point B. Okay, any questions so far? Straightforward, right? So is this thing over here, right? Because we have the common start point. One Q go to the left, the other Q go to the right. That's why you have it as what? 2 Qs. Okay. I don't want you to start dividing the force by 2. Okay, I don't want you to like come here, okay, one left, one right, then just divide by 2. Don't do that. Why? Remember the rules? What are the rules? V and I are what? Constant. Okay, V and I are constant. And that's a critical fact. Okay, if you start messing around, divide by 2 or don't divide by 2, later on you will just forget. Okay, you're like, did I take it off or have I not taken it off? Okay, that will be confusing. Okay, so this is the top. Next, we're going to go into the bottom. So I'm going to copy from here. Hopefully it all goes. So now we are dealing with the bottom part. Okay. So for the bottom, as you can see down here, for the bottom is a what? Is a white flange analysis. Okay, you can see that. So you're going to say that you're going to have shear stress at point A, and shear stress at point A is a white flange, like what we have before. So we